Have you ever just stared at some piece of tech and wondered, what is actually going on in there? Well, today we're going to learn the secret language engineers use to understand any system you can imagine, and we're going to do it without even picking up a screwdriver. Think of this as your official field guide to becoming a system spotter.
So let's start with a little puzzle. On one hand, you've got a guitar effects pedal that makes the guitar sound all crunchy and distorted. On the other, you have a smart thermostat that keeps your house at the perfect temperature. What could those two possibly have in common? Well, they're both what we can call a black box. Something goes in and something totally different comes out.
And that, right there, is the core definition of a system. It's really just any process that takes some kind of input signal. Engineers call it X of t, just to show it changes over time. It does something to it inside that box, and then it spits out an output signal, which they call Y of t. Our mission today is to figure out what's happening inside that box by looking at 5 key traits.
Okay, let's dive right in with our first, and honestly one of the most important traits, linearity. The easiest way to think about this is as a predictability test. Does the system play fair? Is it proportional? So linearity actually breaks down into two simpler ideas. First up is homogeneity, which is just a fancy word for scaling. It basically asks, if you double the input, do you get double the output? A volume knob is the perfect example. Turn it up a bit, the sound gets a bit louder. Simple. The second idea is additivity. This means if you put two inputs into the system at the same time, the output is just the sum of what each input would have produced on its own. No weird interactions.
And when a system checks both of those boxes, when it passes the scaling test and the summing test, bam, we can officially call it a linear system. It's predictable and it doesn't throw any curveballs at you.
All right, time to put this into practice. Let's test a system. Imagine we have one where the output is always the square of the input. So is this system linear? Let's find out.
Okay, now the math here tells a really interesting story. The first equation shows what happens if we add our inputs together first and then run them through the system, so we square the whole sum. The second equation shows what happens if we run each input through the system on its own, squaring them individually and then add the results. And you might remember from math class, those two things are absolutely not the same. The system just doesn't treat the sum of the parts the same as the whole.
So what's the verdict? Pretty clear, right? This system is non-linear. It completely fails our predictability test. Why? Because its response isn't proportional. If you double the input, you actually quadruple the output.
All right, on to our next trait. Now we're asking a totally different question. Is the system consistent over time? In other words, does it behave the same way on a Monday as it does on a Friday? This is what we call the time invariance test.
A time invariant system is one where timing just doesn't change the underlying behavior. Think about a perfect echo. If you clap your hands right now, you hear an echo. If you wait 5 seconds and clap again, you hear the exact same echo, just, 5 seconds later. The system itself, the room, didn't change.
So let's test another system. How about one that multiplies the input signal by whatever the current time is? You can picture this like a volume knob that's just constantly, slowly turning itself up all day long. So to test this, we do a little two-step comparison. For step 1, we delay the input signal before it even goes into the system. What we get out is the current time t multiplied by that delayed input. Now for step 2, we do the opposite. We take the original output and we delay the entire thing. See how in this case, both the time variable and the input signal get shifted back together? The real question is, do we end up in the same place?
And here's the moment of truth. Are those two results the same? Just a quick look tells you, nope. Not even close. That multiplier on the outside is different in each case.
So, the verdict is in. This system is time varying. Its behavior literally depends on the clock. An input you give it at the 1-second mark is going to be treated very differently than the exact same input at the 10-second mark. Okay, our next two properties, causality and stability, are basically just a reality check. For a system to actually exist in our physical world, it pretty much has to follow these two fundamental rules. Causality is super simple. You can't have an effect happen before its cause. A causal system's output can only depend on what's happening right now and what's happened in the past. It just can't see into the future. And stability is all about control. If you put a reasonable, limited signal in, you should get a reasonable, limited signal out. The system shouldn't just explode or spiral off to infinity. We call this bounded input, bounded output, or BIBO stability for short.
And that brings us to our final trait. For this one, we ask, does the system have a memory? Does its output depend on what came before, or does it live completely in the present moment?
A memoryless or static system is like a basic light switch. The light is on or off based only on the switch's position right now. It has no idea what position it was in a minute ago. But a system with memory, a dynamic system, that's more like your car's cruise control. Its current action, whether it speeds up or slows down, depends entirely on your past speed.
Okay, so we've just covered our 5 core traits. Now, let's pull it all together and create what we promised at the start, the ultimate system spotter's guide. This is your quick reference for decoding any system you come across.
And here it is. This is your checklist. For linearity, you ask, does it follow the rules of adding and scaling? For time invariance, does timing matter? For causality, does it need to see the future? For stability, is the output going to go crazy? And finally, for memory, does it have to remember the past? These 5 questions will unlock the basic behavior of pretty much any system.
So why does any of this matter? What's the big deal? Well, this secret language of properties isn't just for exams. This is the actual toolkit that engineers and scientists use every single day to analyze, predict, and most importantly, to design all the technology around us.
I mean, think about it. When someone is designing a 5G network, they absolutely need it to be linear so our signals don't get all jumbled. When they're building an MRI machine, it has to be stable, otherwise you'd never get a clear image. This stuff isn't just theory, it's the absolute foundation of the modern world.
So we've seen how these 5 properties are the essential building blocks for engineered systems. But that kind of leaves us with a huge, fascinating question. Are these 5 properties enough? What other kinds of properties would we need to add to this list to truly define a complex biological system, like, say, the human brain?
Now that's something to think about.